Good morning, everyone. Thank you for joining our webinar and live demo on zero-bug software, mathematically guaranteed. My name is Ashley. I am the marketing manager at TrustInSoft, the leading provider of formal methods-based code analysis tools. So I'm joined today by Vic Sharma, our US account executive, who will be presenting to you some background on TrustInSoft and on formal methods. And Jacob Swalakowski, who is one of our R&D engineers, who will be showing you the live demo of our tool, TrustInSoft Analyzer, in the second half of this webinar. So this webinar is being recorded, and you will receive the replay and the slides in the coming days by email. If you have any questions for our presenters, feel free to ask them in the chat, specifically in the Q&A section on the right-hand side of your screen, and the presenters will answer your questions at the end of the webinar. So let's go ahead and get started. Vic, are you ready to begin?
Thank you, Ashley. Good morning, good evening, everyone. Thanks for taking the time to join us for this session. In 2015, as part of a DARPA challenge, a team of hackers were given direct access to an unmanned military helicopter known as the Little Bird. Think about it. A group of hackers, contrary to what we would expect, were actually allowed to access part of the helicopter's computer system. Their goal was to hack into the onboard flight control system software and take control of the unmanned helicopter. Despite their best efforts over the next several weeks and with almost unrestrained access, the hackers could not penetrate Little Bird's defenses. You may ask, how could this happen? This happened because DARPA had secured the key parts of the Little Bird's onboard flight control computer software and made it unhackable using formal methods. Next slide, please. So what are formal methods and why are they so powerful when it comes to guaranteeing absence of bugs? Simply put, formal methods are methods and techniques that rely on math and logic by first formulating the mathematical equivalent, or as we say, a mathematical model of a given software program and its underlying source code, and then by comparing it with its specifications, assessing whether under a given set of input values or for all possible input values, the program will deviate from what it is supposed to do or not. Because the code is analyzed like you would prove a mathematical formula, there is no ambiguity in the results. There is absolute certainty that the results are true. There's an assurance that the program does not have an undefined behavior. Now, undefined behaviors, as you know, are precisely explained in C and C++ standards. And that is indeed the power of formal methods when it comes to code analysis, which is to be able to guarantee that there are no bugs. Next slide, please. And that is the assurance that TrustInSoft is delivering to its customers in many industry verticals, including aeronautics and space, defense, automotive, specifically autonomous driving, telecom, IoT, and consumer electronics. Our technology, based on formal methods, has been built on over 30 years of research and development in mission-critical systems. And it's not just the customers who have benefited from assurance. The technology has been recognized by federal bodies in US and Europe. For example, in the US, NIST in its report to the White House highlights how through sound analysis, our technology could prove the absence of bugs in a critical stack, such as an SSL, which was indeed a unique and first of its kind result. We have worked with the Linux Foundation, and we were recognized as one of the most promising startups at the RSA conference. Next slide, please. Now, through the session, we not just want to talk about formal methods and how they bring certainty and exhaustiveness to code analysis. What we want to highlight is the fact that their underlying power can be successfully delivered through automated tool such as TrustInSoft Analyzer and the ease of use that comes with it, like we have delivered to many customers representing many verticals. The technology that we used originally for validating the safety critical code in an airplane, which is the one you see on the left side, which was one of the verticals we started in, is the same tool and technology that is now being used by our customers to secure the embedded code on a consumer device, such as a game console or a mobile phone. And it's the same tool that is being used by our customers in autonomous driving to verify safety and security properties of the embedded code on the vehicle. So as you can see, it's not just limited to certain domains, but can be widely used in many verticals. Next slide, please. And that is our core value proposition. TrustInSoft Analyzer delivers a mathematical assurance through formal methods and by leveraging advanced static and dynamic analysis techniques that your C and C++ code is reliable, robust, and of the highest quality. Thanks to formal methods, there are no guesses or list of potential bugs when you analyze your code. What you get is a mathematically verified and validated code to ensure that it does what it is supposed to do. So you can be rest assured that it is safe and secure. Next slide, please. So what does formal methods bring to the table? At the core of sound analysis using formal methods is the ability to detect all undefined behaviors. Now, undefined behaviors, as I mentioned earlier, are precisely explained in the C and C++ standards. They can be very complex, and if not detected early on, can lead to serious consequences such as unpredictable results or software crashes, which in turn can lead to even bigger problems. So by guaranteeing absence of errors such as the ones listed here, for example, a buffer overflow or a division by zero error, early on in the software development life cycle, you can address and eliminate potential issues that might arise during runtime. By mathematically proving program correctness, you can ensure that the code performs the way it is supposed to. Next slide, please. So how do we compare with other source code analyzers? Well, let me highlight a few distinct points that differentiates us from most of the tools. Unlike traditional analyzers, some of which you see here, that are unsound, that is, they're unable to report all potential problems, TrustInSoft Analyzer performs sound code analysis by ensuring that if a bug exists in the code, the tool will not sit quiet and it will indeed raise an alarm. And unlike other tools that perform primarily syntactic analysis, merely searching for patterns or suspicious code constructs or coding rule compliance to deliver a list of potential bugs that may or may not be real and a large number of false positives. On the other hand, TrustInSoft Analyzer applies formal methods and performs a deep semantic analysis of the code, essentially analyzing its behavior um, and checking execution for all possible input values to identify issues and guarantee absence of all undefined behaviors. And this results in code that is of very high quality. Next slide, please. The real differentiator, though, is our unique methodology that incrementally and progressively helps you achieve a high code quality. This is our three-phase approach. First stage is what we call as an interpreter mode or level one. At this level, we simply replay the tests. The analyzer exhaustively detects all undefined behavior. It'll help you find more bugs with your existing tests and even subtle bugs which otherwise you may have missed. In other words, it helps you get the most out of your time that you've invested in your existing tests. Every bug identified is a real bug, zero false positives and zero false negatives. What you see is indeed real, and you get a mathematical guarantee that all undefined behaviors are detected for your existing tests. Moving to level two, which is the analyzer mode, you can progressively increase the number of tests that you can do to reach an exhaustive coverage by generalizing the inputs, and which is what you'll see shortly in our demo, what we mean by generalizing the inputs. You can conduct an equivalent, essentially, of a very large number of tests to go even further and mathematically guarantee that your code does not have any undefined behavior for all the inputs. You still have zero false negatives, and you can achieve up to 100% coverage on your critical tests. So together between level 1 and 2, it covers about 80% of our users. For the rest, in extremely safety critical domains, you can even go further to do functional proofs, proving that a piece of C and C++ code is exactly doing what it is supposed to do. It takes a little bit more time, but through formal proofs, you can see if your architectural vision, your software specifications are enforced on the code or not. Next slide, please. So, in essence, by combining the power of formal methods and the value they bring by making their usage easy, with the benefit of static and dynamic analysis techniques, the ease of use through an automated tool, um, and the fact that you can do it in an interactive manner at each step. You're in control and following what's going on. We deliver a very powerful solution. Next slide, please. So how do we empower the developers and testers? We do that by enabling them to exhaustively find and fix all undefined behaviors, including the most subtle ones that they may otherwise miss, and ensuring absence of crashes and achieving deterministic behavior of your C and C++ code, by boosting the software coverage, by performing equivalent of a large number of tests with one generalized input, so you can progressively reach a high code quality, and finally get a mathematical guarantee on absence of undefined behavior, thus ensuring your safety and security, ensuring the safety and security of your code. Next slide, please. So what are the primary drivers for our customers using TrustInSoft Analyzer? As a starting point, all our customers have very demanding requirements for code safety and security, either due to compliance requirements for specific certification standards, such as in regulated industries, such as aeronautics, or due to stringent code validation processes, or driven by risks in a brand or image if a security flaw is uncovered in the field post-production, and how that may impact field support costs. Given these requirements across our customer base, there are three primary drivers and the value TrustInSoft delivers to address these drivers. First, prior to putting the product in the market, how we can help the customers improve operational efficiency in their software development lifecycle. Second, how positioning security and safety as a product feature, thanks to the mathematical guarantee that the analyzer brings, we can help the customers generate more revenue opportunities. Number three, controlling the financial risk if and when an issue occurs in the field. Next slide, please. And I'm going to take a few examples here. First example on improving operational efficiency in the software development lifecycle in a regulated industry, in this case, aeronautics. We compared the software verification process with and without the analyzer using quantified data. The customer here was a tier 1 provider to the aeronautics industry. The stack was a communication gateway software. The analyzer was used as stage 1 and stage 2, which is the interpreter mode and the analyzer mode. And using the analyzer, the verification time was reduced from 4 months workload to 1 month workload, essentially divided by 4. And at the same time, the software test coverage was significantly improved because the analyzer enabled performing equivalent of a very large number of tests. Next slide, please. The second example under improving operational efficiency is in a less regulated industry, consumer electronics. The stack here was the software deployed on a set-top box. The objective of this customer was initially in the first stage to evaluate the capability of the tool to help them identify complex issues. The customer provided us with a previous version of their software where 2 of their engineers spent about 10 man days identifying one bug and correcting it. But when they performed the same analysis using TrustInSoft Analyzer, it took them 2 hours to identify the bug. So here, as you can see, we enabled the customer to reduce the effort by 40x. So these are the 2 examples of how we can help customers improve efficiency in their software development lifecycle prior to putting the product in the field, boosting the software coverage, and spending time only on the real bugs results in efficiency. Next slide, please. In the second category, which is how we help customers generate more revenue opportunities. Now, this is a customer, a tier 1 provider to the rail industry, a very demanding industry in terms of safety. Here, the software is actually going to the market. This TrustInSoft Analyzer was used on the embedded software that manages inputs coming from multiple sensors. It was a large stack, had about 300,000 lines of code. And the objective was to focus on guaranteeing the safety of the critical functions. The customer used the analyzer mostly at level 2 to guarantee there was no undefined behavior in the source code. The code had deterministic behavior and never crashed whatever the inputs, and that they could achieve 100% coverage on all the critical functions. The mathematical guarantee and this level of software coverage was actually positioned as a differentiator for their customer versus other competitors. And this was a key element, the fact that the customer could guarantee the safety of their code with this level of coverage and demonstrate it was a key winning factor. So positioning safety as a product feature is an enabler for increasing market share. It can also be an enabler in some cases to position your product with a price tag. And in some cases for our customers to get into the market at the right time to grab opportunities um, as well. And we can enable that by achieving the right level of code quality. Next slide, please. And finally, once the product is in the field, one of the worries of our customers is to control the financial risk associated with bugs or flaws. In this case, the customer is a provider in the smart meter industry. They're using the analyzer on a stack deployed on a smart meter, measuring the energy consumption of their customers. They use the analyzer at level 1 and level 2 with the objective to detect and fix all critical bugs and increase significantly the coverage of their test, and were able to reduce their field support costs. Why is it important for this customer? Because a part of the software in the smart meter cannot be remotely updated. So if a bug is identified in this critical part, which measures the customer's energy consumption, their customer's energy consumption, it can only be updated by a technician going in the field. And as you can see, that adds to the cost in addition to having a negative impact on the brand and the image. So these are the three business drivers prior to having the product in the field, how we can help customers improve their efficiency in software development lifecycle and verification process, how we can help the customers position themselves with security and safety as a key feature to gain market share or price premium or secure time to market sensitive opportunities, and finally, how we can enable them control the financial risk once the product is in the field. Next slide, please. And just before I wrap up, TrustInSoft Analyzer can be installed on a dedicated server, either on premise or in your cloud, public or private cloud. It can be accessed through a web browser or a command line interface, and can be integrated to your existing DevOps and your CI/CD tools. And next slide, please. I'm going to leave you with this large number. As you can see, in the following demo, you'll see how the analyzer can perform equivalent of these many number of tests. Over to you, Jacob. Thank you.
All right, thank you, Vic, for that presentation. So Jacob, if you can go ahead and share your screen. And in the meantime, I would just like to take a moment to remind you that if you have any questions, don't be shy. You can go ahead and ask them in the chat. So thank you, Michael, for your question. We'll go ahead and get to that at the end. If anyone else has any questions, feel free to ask. And it's all yours, Jacob.
Okay, thank you, Ashley. Hello, everyone. So I will show you now how I can do this huge number of tests that Vic just talked about right here on my laptop, which is not some kind of powerful supercomputer, but just a standard Linux office machine. And well, this is possible because we don't actually do so many tests, but we do something equivalent thanks to the power of mathematics, and more specifically, by applying formal methods. So our support for this demo is this little toy cryptographic library, which is based on Caesar cipher. Maybe you know Caesar cipher or not, but it's a very old and naive encryption technique. And I will show you how I perform exhaustive analysis on this toy cryptographic library. So Caesar cipher, basically, how does it work? We take each letter of the plain text and we apply an offset to this letter. For example, if the offset is 3, then the letter A becomes D, because from A we have B, C, D. So offset 3. And so this is pretty straightforward. And here our library is quite small. We have just these 3 files with code. We have Caesar H, which is the API of our library. We have Caesar C, which is implementation. And we have main C, which is the test suite. So starting with Caesar H that you can see here, it's very straightforward. Yes, we have the encrypt function and the decrypt function. The encrypt function takes a string and takes a number here, which is the right shift to perform on each letter. And the decrypt function does the opposite, so it will perform the left shift on each letter. So let's see now what is the implementation of all these. So we have another function added here, the absolute int function. So in this function, I take an argument x, and if x is below 0, then I return the opposite of x, and otherwise I return x directly. Pretty simple. Now I have my Caesar encrypt function, which takes a string and a d, an integer. And what do I do here? Well, first I compute the shift value by computing the absolute value of d. Next, I declare and initialize my index variable I. And then I go to my main loop. And in my main loop, what do I do? Well, until I have arrived at the end of the string, which is the 0 character, always used to terminate strings in C. So for each character in the string, if it is not a space, I will simply add the shift value to this character. So I will shift the character to the right in the alphabet by this number. And then I continue until I reach the end of the string. Pretty simple. At the end, when I reach the end, I also add a 0 to terminate the encrypted string, and I return it. The decrypt function is exactly the same. The only change is that here we subtract the shift value instead of adding it. So as you can see, this is pretty simple. And the last part of this code, because you have just seen the whole library. So this is the test suite that we add to it in file main C, and then here you have this function that performs a test, where I take a shift value and I take a string, and I basically encrypt the string and then decrypt it. And I print everything that's going on in the meantime, so I can visually compare this to expected results. And my test suite contains 2 tests. So both are based on the same string, people of Earth, your attention please. First is performed with shift -3, and second one is performed with shift 7. That's all. This is a very small test suite, just 2 cases, but actually for this very small library, it's pretty sufficient. It covers 100% of statements in the library. So not so bad. And let's see what happens when I actually compile it and run. So it seems that everything works fine. I have my 2 tests. I have the string, people of Earth, your attention please. It's encrypted, and then it's decrypted, and it gives me the same string as before. Seems right. Also, I can see that from P is encoded as S, and here between P and S, I have E, Q, R, S. I have 3 characters. So it's fine. The absolute value here should be 3, and between P and W, I have 7 characters. So everything seems to be right. Well, let's see what happens when I run the analyzer, or more exactly, the graphical interface of the analyzer, which runs in a web browser. So here I will see that the analyzer tells me that there are 2 undefined behaviors found in the program. Okay, let's see what's going on here. First, on the right, you can see the source code pane. So this is the original source code of the program. This is exactly what I have just showed you before, the same thing. And here in the middle, what you can see is the same code, but in an extended interactive version. So basically, there is some information added here, and this is clickable. So I can get some more information by clicking on things. For example, here I can see that the red stuff is that code. So the code which will not be executed. And here I can see these 2 comments added by the analyzer. So this is how the analyzer talks to me and tells me about undefined behaviors. it inserts this kind of comments into the code. Of course, it's not inserted into the original code, but this interactive one. How do I read this? Well, the first one tells me that buff here, which is the access to the variable buff, can be an invalid pointer at this point of program. And the second assertion here says that buff plus I, accessing buff plus I can be an invalid memory access. So these are two separate problems happening on the same line. Okay, so now I can use the features, different features of the analyzer to understand what is actually going on. For example, I can click on buff and I can find where does the value of buff come from. And the analyzer will tell me, well, at this line, I allocate buff, I allocate a buffer of memory for buff. And here I can see what are the values of buff at this point in program. And I will, actually, it can be either a null pointer or an allocated buffer of memory. And indeed, I can see that here, after performing this, this allocation, yes, the buff can be a null pointer on an allocated buffer. So I understand what is going on here. Basically, I forgot to check if the allocation succeeded. Maybe the allocation failed, and I have a null pointer here. And here I'm accessing this null pointer, which is obviously undefined behavior. The second problem is coming from different things. So I can look at I, at the values of I at this point of program, and I can see that before this statement, it goes from 0 to 33. And after that, the analyzer tells me it goes from 0 to 32. So there is a problem with value 33 here. Why? Well, because I actually allocated a buffer of fixed length of 33. So its indices go up to 32. Thus writing at buff plus 33 is out of bounds access. It's an invalid memory access, and actually writing in an invalid memory write. So these two warnings come from these two different reasons. Buff, this first warning comes from the fact that buff can be a null pointer here, and the second warning comes from the fact that I can it can be a buffer overflow. Okay, so the frightening thing here is that, as you can remember, before I performed the test, here you can see, and it seemed to work. So it didn't end in a segmentation fault or something like that, even though there was actually a buffer overflow problem here, and I accessed invalid memory. So this is a bit frightening, because it means that I didn't find this problem by performing a test, and it's a pretty serious problem. So this kind of problem can lead to serious exploits or safety problems. And also other tools, many other tools like Valgrind, for example, will not find these kind of problems. So already here, when you are just replaying this kind of tests in the analyzer, you can already see the added value that we give here. Okay, but here I only perform an analysis on two different inputs, on two different shift values, and I promise you a lot more. How do I get to this huge number of tests that Vic mentioned? First, instead of checking just two different shift values, I will check all of them. So let's suppose that I corrected the problems that were mentioned before, and I add a new test case to the analysis, the third one, where I will check for all the possible shift values. So here you can see I declare a new variable, user shift, and I use this special function, this make unknown. I give it the address of user shift, and I give it the size. And after that, the user shift variable becomes abstract. So basically, it can have any value in the int type possible. So it's not a single value anymore. It's a whole interval. It's not a random value in this interval. It really represents all the possible integers. And also, I can analyze it like if it was a concrete value. So I can still call GenTest with it. Okay, so let's see what happens when I run the analyzer on this example. And I will see that it has actually found another undefined behavior here in the function absolute int. So this is a signed overflow, which happens when I try to compute minus x. Why does it happen? Basically, on a computer, there is more negative values than positive ones, usually. So for example, if I have a 8-bit integer, the minimal value is minus 128, but the highest value is plus 127. So I cannot compute minus 128 because it's not representable. And this is exactly what happens here. So when I try to compute minus the minimum value of integer, then I have a signed overflow, undefined behavior. So of course, finding this kind of problem here was possible because we checked all the possible values of an integer. At this point, you can see this is the whole interval of values of x in this branch of the if function. So what do I do here? Well, it depends. What do I want to do? I can either try to treat this case in some way, this case of minimal integer, or I can decide not to include this case. And this is exactly what I will do. I will remove this value from my analysis because I suppose that this function was never supposed to handle this value. So I decide not to test this case. And how it is done, it's pretty straightforward. I simply add this if statement here. So I remove the minimal integer value from my interval. And I do exactly the same thing as before. And you can see that this will work. And it shows a little bit how the analyzer works on the inside. So it is actually capable of understanding what happens in the code, what are the semantics of the code, and understand that in this branch of if, on this branch of if, the user shift variable will only have these values. So the minimal int value is removed. And as you can see, here I have green ticks on the left now, which means that there is no undefined behavior found in the program. So this already, what happened here is that the analyzer gives me a mathematical guarantee that for this huge number of inputs, so this is 2 to the power of 64, all the possible integers, well, minus 1, minus this one value. So for all these values of inputs, there is no undefined behavior happening in the program. Okay, so now the last step here. In addition to testing all the possible user shift values, I will also try to test all the possible strings of this size, and not just my string people of Earth, your attention please. In order to do that, I add yet another case to my analysis. So now that's the fourth case here. And I use my thisMakeUnknown function on the whole string, giving it the size, the length of without the last character in the string, which is the terminating 0. So I keep the terminating 0, but all the other characters in the string before, 38 characters here, are now abstract, any possible characters. I still keep remove the minimal integer value from user shift, and I perform my analysis on these inputs. As you can see, it's well, pretty quick. This is done now. So now I'm performing an equivalent of this huge number of tests. I also have green ticks here. So that basically means that the analyzer has proven that for the value of shift, which is all the possible integers without 1, so it's 2 to the power 64, and for all the possible strings here, which are 38 characters, abstract characters. So this is, each character can have 256 possible values, of course, and I have 38 of them. So this is 256 to the power 38 times 2 to the power 64, the huge number that Vic showed you before. And for all of these inputs, exhaustively, I have proven that there are no undefined behaviors in the program. Okay, so that's the end of this demonstration. Of course, this is a very simple case, a toy example that was made in purpose to explain in a simple way how the analyzer works. There are more complex cases that we can show, like for example, the ARM's SSL TLS stack analysis or Goodix driver analysis, which is a model of Linux kernel. But this is for another time. So.
Great. Thank you, Jacob, for that demonstration. So we have a few questions in the chat here. So, yep, Vic, if you want to come back as well, I'll let you guys decide how you want to answer. But here is our first question from Michael Watts. So, when thinking about input ranges, how can this be applied to embedded software where, say, a voltage is being measured?
All right, well, I'll take a shot at this. Well, it can definitely be applied. In fact, we excel on low-level software, embedded software. In this case, it can be applied to voltage. Let's say if the voltage is measured by a sensor, in that case, mapped to the memory or the register. But definitely it can be applied. And as I said, many of our customers use the analyzer on embedded code, low-level code. Anything you want to add to this, Jacob?
Yes, so you're right. Basically, this is done in a very similar way to what you have seen in the demo, where I rendered some values abstract. So if there is a variable that is used for the voltage, basically, which comes from the sensor, I can perform analysis where I suppose that it can be any possible voltage that is measured, and do just that. It can be an integer, it can be a float value. A lot of different things is possible.
Okay, great. Next question that we have here is from David Fleming, who would like to ask, what do you mean by code semantics? So I think, Vic, this was in your presentation, if you want to...
Certainly. Well, code semantics refers to analyzing the behavior, what the code will do versus its style, or if it follows the rules of the grammar of the programming language. So essentially analyzing the executions of the code, the behavior of the code, given an input value or a range of input values, a generalized input value. So that's what we mean by analyzing the semantics of the code. Anything you want to add just to that, Jake?
What I can add is that, for example, for C or C++, it's the C standard or C++ standard which determine the exact semantics of the language.
That is exactly right.
Okay. Next question is again from Michael Watts, who would be interested to see how math considers memory allocation, such as undefined behaviors like buffer overflows or memory leaks, etc. Maybe a question for Jacob?
So the mathematical model of what's going on in the program, of the semantics of the program, include, of course, the model of memory and memory allocation. And as you have seen in the demo, there was kind of a buffer overflow happening there, which we found. We can also find memory leaks in the program. They are not strictly speaking undefined behaviors, but we can the analyzer can be used to find them too. So yeah, this is possible.
Okay, next question from David again. How can you achieve the number of tests that you indicated on the previous slide? So I think maybe a question also for Jacob.
So basically, the number of tests, as I already calculated, it comes from the fact that we test all the possible shift values, and these are all the possible 64-bit integer values -1. So this is 2 to the power of 64. And the other part comes from the fact that we are testing all the possible strings of size 38, which gives us 256 to the power of 38 possibilities, and all that gives us this number. And it's if you mean how is it possible to achieve this number? Where we use it thanks to the fact that we do not perform all these tests one by one, but where thanks to the mathematics and power and formal methods, we can use the whole intervals in the same time. So it doesn't take the incredible amount of time that it would need to take if we would do these tests one by one.
Okay, thank you. And our last question for the moment is from Edgar. He wants to know, is it necessary to modify well-known modern software process development in order to take advantage of the set technique or method enabled by this tool?
Well, yeah. So no, it's not. In fact, it's the tool's agnostic. You don't have to really modify anything in terms of your software development processes in order to take advantage of the technique. Thanks to formal methods, it works very well from your low-level code all the way to applicative software. It's pretty agnostic to the style or how you write the code. So with the goal of ensuring the robustness of your code, really, you don't have to necessarily modify any of the software development processes. Anything you want to add to that, Kuba? I think I may have covered it. Please go ahead.
Yeah, I think you basically covered it. And the proof that you don't have to change your process is that sometimes we apply the analyzer at the end of the process, so when the program is already there and running for a long time. Some open source cryptographic libraries, for example, real ones, not like this example, and we can check and find bugs simply. So it doesn't have to be done in the middle of the process. So it doesn't actually interfere in any way. It can be done in any part of the process, or as a continuous integration.
All right. Well, thank you for attending this webinar. We hope that it was informative for you. You'll receive the replay and the slides in the next few days by email, so keep an eye out for that. But in the meantime, if you would like some more information, don't hesitate to reach out to us or visit our website, which is TrustInSoft.com. So thank you and have a great day. Bye now.
Thank you, everyone.
Thank you.